So good morning. I think that Misha Dollar needs little introduction. He is the head of Intelligent Energy Group here at CTTC, and is a well-known expert on topics as wireless sensors, cooperative communications, energy efficiency communications, and many other aspects on which he's got a long record of quality publications. So I'll leave the floor to Misha for the presentation of today.
Thanks, Pep. Okay, good morning, everybody. Today is our SON day, Self-Organizing Networking Day. And we had a little change in agenda, actually. So I'm replacing, actually, the Qualcomm guys, but using a presentation, modified presentation of my MO1. So this is what we're going to be doing today. Now, the idea of the day is that I'll be giving an overview, really the building blocks of the self-organizing networking within 3GPP and our community at large. And as we go along the day, we will be populating some of these building blocks with very specific algorithms. So Ana Maria later on will tell you about very specific cognitive and dositive approaches, how to facilitate certain self-organizing networking algorithms. Then Ali will also give a general framework, but he will also give some more concrete algorithms, and I will finish the day with the general protocol suite. Now, before delving actually on the self-organizing, I would like you to understand a little bit what is happening with our systems, or what has been happening with our systems as we have been rolling them out over the past 2 decades. And something very important to understand is the notion of the degree of freedom. Degree of freedom essentially means, you know, the amount of parameters you can tweak. They don't have to be independent. They can be very dependent. And actually, when they become dependent, this is when the whole network, the whole problem starts. Now, the parameters you can think of is at which power do I transmit? Which frequency do I use? To which cell do I hand over? What time delay do I wait until I hand over? Etc., etc. So this degree of freedom has been increasing ever since we started rolling out GSM. So if I normalize my whole degree of freedom notion, meaning the amount of parameters I can tweak in my system to make it really run with respect to GSM, which will be my value 1, and we go along in history, Edge, UMTS, LTE, LTE, etc., we see that this amount of parameters just goes up very quickly, exponentially, actually. Okay, so that is a logarithmic graph here. And if you look through the documents, you figure out that every time you introduce a new system, the amount of degrees of freedoms you're introducing, essentially, is increasing by a factor 20 to 30. Now, also every time you introduce a new system, actually, you are having a cell coverage which is significantly smaller, and the average is that every time a new system comes, you have, for the previous old 1 base station, you have 4 new ones. So what you figure out is that your degree of freedom per area is increasing every time you introduce something new by a factor of 100. This is 2 orders of magnitude. Now, that does not seem to be a big deal if you go from GSM to Edge. It starts to become a big deal when you go to UMTS, and I can tell you that because I've worked for a optimization company in London for a few years, which did cell planning for UMTS. It was a pure nightmare. The sheer amount of parameters you can tweak, optimize, look at, etc., is horrendous for an engineer. What we want is something very simple. Ideally, what you want is a switch. You switch on, it works. If you don't want to work it, you switch it off. You don't want to tweak all the time in dependency what's going on in your cell. So things get complicated. HSPA, the high-speed packet access, things even more LTE, and we don't talk about LTE. So that's an enormous amount of parameters you can tweak to make your system work. Now, you can always leave your system as it is, and it will work, but if you want to make it work better, more optimally than you have it right now, then you need to do something about it. So degrees of freedom goes up. What does it imply? No, just to corroborate before I go to the implication. You know, we had this slide a few times now these days. This is what we have today. So it is not just a increase of degrees of freedoms you can optimize power, handover, etc. of a single technology, but also there are various technologies. You have GSM, you have UMTS, and you will have LTE LTE at the very same time operating. You will have sensor networks, you will have femtocells. Femtocells, you have maybe hundreds or thousands of femtocells per macrocell coverage area. So suddenly you understand you have a heterogeneous network with loads of parameters you can tune and tweak. And if you have a lot of parameters to tune and tweak, things can go wrong. And the more parameters you have, the higher the probability that things go wrong. It's a very simple insight from system design. The probability that your system goes in outage or that your system fails is essentially directly related to the number of components you have, okay, and the probability of a single component going in outage. So I'm taking one of the typical slides from this operational design. You plot, you know, the probability of failing of a single component versus time in years. Having a single component, and component can fail with a certain failure rate they are given there. It's just an example to give you an idea. That probability over years goes up. Now that is a single component. What we just established, we have 10 to the power 12 components or degrees of freedoms actually interacting and doing things. So the probability that something goes wrong in your system, if you don't do anything about it, is basically almost 1 from day 1 as you deploy your network. Okay, so no matter how hard you try, no matter what you do, your system will not work on your first day. And I can tell you, UMTS was a great disaster on the first weeks of rollout, simply because of that single degree of freedom called power control. CDMA is actually a pretty lousy system, so I personally don't really like it. But and one of the problems is that, you know, one of the beautiful things is you have a single frequency network, and one of the bad thing is you have to have a very, very good power control in place. So if you have a single user in place, everything is good. But the moment they introduced a second user, and this happened actually with Vodafone right here in Castelldefels, a friend of mine was testing that, introducing a second user just screwed up the whole system. Okay, so until they managed to dominate the power control to really be able to stabilize the system, and CDMA, that is very important, it took a very long time. So that was just this single degree of freedom. We're not talking about handover here. We're not talking about 3 or more users. So here you go. Understanding that a lot of components, a lot of degree of freedoms means a very high likelihood that things go wrong. This has enormous impact on the finances. Okay, if you don't do anything about it, people get unhappy. If you travel, you talk on your phone, and the handover fails, and you just get your call disconnected, and you have to redial, this annoys you. You do that 10 times, you do that 20 times, and then you're ready to change operator to see whether the other operator is actually doing better than the one you're at. This is called churn. So what the operator is trying to minimize is that people get unhappy and change operator. So what they want is that your quality of experience is very good. In fact, the quality of experience of using the wireless network should be so good that you just forget that it exists. This is ideally what we want to do. That's why also a very big research branch lately has embarked on the notion of quality of experience, not quality of service. Quality of service is a very technical thing, but you know, the machines don't pay the bill. It's the people who pay the bill, so the quality of experience is in the end what really matters. So therefore, if you don't do anything, your system is lousy, people get unhappy, they're going to leave. Alternatively, if you do something about it, but you use people, your own staff, to repair the mistakes in the system, this is going to cost you a fortune. Every time there's, let's say, a problem with an antenna tilt, there's a problem with a power control algorithm, there's a problem with a cell ID association, you don't want your staff to go to every single base station connect with the WAD or whatever and start reprogramming the base station to see until it works. It's just not scalable. So therefore, we all understand automizing the whole process is something we should really be doing. And this is essentially the notion and the justification of self-organizing networking, where we have actually two components. The SON is doing two things. The first thing it does, it is replacing really silly manual labor. Okay, a very silly manual labor in the networking rollout is you go there, you place the base station you put the base station in place, something you still need to do. But then engineers spend a lot of time there on site configuring the whole thing. All right, so they're actually connecting to the eNode B. They're seeing what kind of coverage it sees, how does it relate to the neighbors. It is you need to configure the cell IDs, you need to configure the tilts, the powers, etc., etc. So they spend a considerable time really trying to make a single eNode B up and running. And there might be thousands of those in Barcelona. And you introduce a new one, so you screw up maybe an old one, so you have to go back to the old one, you have to reconfigure. Your eNode B maybe goes in outage, you have to go there, you have to again physically go there. It's very expensive. It's very, very expensive. In the end, you spend more time and therefore more money repairing your system, maintaining your system, than actually having paid for the capital of installing that. Now, this is something you really don't want. You wanna have a fair capital expenditure, and you want to have a very close to zero operational expenditure. That's the only way you can scale. And that becomes more and more important with the latest trend that we are decoupling data rates from revenues. So data rates go up exponentially, and the revenues are flattening out. Now, that's pretty bad news. It's pretty bad news, actually, for the cellular operators, and we as a user, we profit from this, but at the same time, we in this audience here as R&D engineers, we suffer from that. Okay, so let's not be mistaken, because everything the operators lose out now on gains is something which does not flow back into the R&D, so it doesn't flow back to us. So, you know, it's a trade-off here, and clearly all of our friends out there would like to have as cheap mobile data plan as possible. But in the end, you know, there's no free lunch. Somebody has to pay for the party. So here you go. So that's very important. You want to really minimize the manual process. But there's another opportunity for SON. Self-organizing networking algorithms suddenly can do things which humans have not been able to do before. They can adapt things in real time. It doesn't mean at millisecond level. It can mean at minutes or hours. So it's pseudo real time. But the system is able to adapt to conditions, real-time conditions, which are happening. So if Barcelona plays football, there's a lot of people going to the Camp Nou, meaning there's a lot of traffic there. Okay, so it will require reconfiguration, essentially, of the cellular system in that area, and this is what they are literally doing today. So therefore, you can also take over, the SON algorithms can take over functionalities which have just been unprecedented before. Having said this, the automation in the network is not new. Okay, so automated networks is something, a notion which is 100 years old. It started essentially, you know, with airplanes, with satellites, you know, all these space missions, etc. You have to automize it because there's no human up there. So the whole branch of that science is not new. Having said, you know, of entering this into the industrial world of the telecom, 3GPP, etc. Now this is new. This is something which is really unprecedented, and there's an opportunity for us as engineers really of making an impact in this area. And my talk today will be a little bit to show you what 3GPP is thinking of SON today. So maybe you get inspired, you can use maybe some tools you will be hearing later on during the day, apply them to very specific problems which have been set out. So I'm not going to talk about the solution. I'm going to talk about the SON architecture and the SON problems, and less about the solutions. Now, the elements of SON. different people have different understandings, so the weight of all these elements will be different to different people. There's clearly an element of distributed in there. Okay, so if you optimize a whole network, it is very unlikely that you are able to optimize your network in a complete centralized fashion, even though we understand doing it in a centralized way is the only way of making it truly optimal. Okay, only if you have the full parameter set from your whole network decided upon using some form of centralized decision making. It doesn't have to reside physically in the very same place, but that's the only way of making your system work, run, and operate in an optimal manner. There are problems there, and I'll come to that. So therefore, you know, people tend to think about SON as something which needs to be distributed. Not necessarily, but there's a notion of distribution. It has to be autonomous. Clearly, it has to run on its own. Autonomy means, you know, there's no human intervention, so you really want to make it run on its own without a person going there and tweaking parameters. There's an element of intelligence in there and optimality. So these things go a little bit along. So you can have a very good automated, a very good distributed, so easily scalable system, but it may just be very far from optimality. Might be a very lousy system. What's the point? Okay, what's the point of having a completely suboptimum system running, even though it's running on its own? You want something which is close to optimality, maybe not really at the optimum point, but good, very good. And to achieve that, you need a degree of intelligence, cognition. We will hear about this a little bit later, but you know, I've been working now in this area a little bit, and I was surprised that, you know, we have not been able to produce a clear-cut definition of intelligence until today. So the artificial communities have been working on it, cognitive machine learning, game theory, etc., etc. We've seen it all, 60, 70 years of R&D, of really high-profile engineers, mathematicians, physicists. There's no definition. We don't know. Okay, we have no notion of intelligence. We have a notion of being able to measure it. You can do your IQ tests, etc., but we don't know. So a definition I like personally very much is, you know, to say a system is intelligent if it is able to operate under conditions it was not originally designed for. Okay, so that is it's a very general definition, but it gets you the notion that just doing threshold-based decision is not good enough. Threshold-based decision means, you know, I'm going to hand over this user to that user, this user from this base station to that base station, if the signal to interference noise ratio falls below a certain threshold. This is threshold-based decision taking. There's no intelligence in there. Deterministic. Okay, if your algorithm just does, or your power does something really funny, your algorithm will fail. So to be able to survive in a condition it was not designed for, you need to adapt, you need to learn, you need to build intelligence on prior observation. And this is what all cognition is all about, and we're going to be hearing about this a little bit later. So I do believe that there's a true scope for cognitive elements, but true cognitive, not the false cognitive, not this decision-based taking, but the true cognitive algorithms in the SON framework, even in industrial context. So yes, SON is not equal to SON. The different algorithms, some are good, some are better, some are lousy. What I said before, you want is a good management, yeah, because you may have really good components. You may have a fantastic LTA physical layer. You may have a fantastic bandwidth available, but if you're not able to manage that, it's for nothing. Okay, there's no sense on having all these capabilities and ability if you don't get it work together. It's like having a team under you where every individual is very good, but as a team you just don't get it going. It's the same story, nothing else. So how does it work in cellular networks? It's very simple. In fact, everything is very intuitive. Okay, there's no magic to this. Thousands of engineers before you have learned it, so you will learn it as well. It's very simple. Before you actually roll out your system, you plan it. And in dependency how much efforts you spend on planning, you might be able to do less efforts in the deployment and in the actual optimization of the system. But then what you do, you plan. Then once you've planned it, you go to the field, you deploy what you need to deploy, you ramp it up. Okay, so that is the this deployment phase. And then you get it going. And you see, you know, maybe I've put my base station close to a train station, so there's a lot of traffic in the morning coming, so I need to configure. I'm configuring on the run, I'm optimizing it, it's getting better over time. Now, there might be an outage, whatever, so we have to maintain it, we have to heal it, etc. So this is essentially what we're doing today. And here's the opportunity for my SON. So there's an opportunity for automizing all this individually or as a whole thing together. Okay, so you can do an automated planning. It's a science which is in about now 5 or 6 years old. You can do the auto configuration. You can do the self-optimization and then the self-healing. And this is essentially what the industry has been looking at in the past years, to go through all these steps, and we're going to be dwelling on that a little bit later on. So what we're going to do is I'm going to show you now in this presentation where and why this SON notion has come from in the cellular world. Okay? Then we're going to be talking about some architectural elements, we're going to be talking about some features, and then the functional details, and we call it the end of the day. So where it all came from, really, and it all started about now 7 years ago. In 2006, there was an alliance formed, NGMN, Next Generation Mobile Networks Alliance. It was formed, it's an alliance formed by operators. Operators are those who essentially own the whole value chain of deploying, exactly the graph I'd shown you before. They need to plan, they need to deploy, they need to optimize, they need to maintain the system. So they knew very, very well the daily operations of having this system up and running. And they said, okay, let's get together and try to elaborate on a set of features which needs to be looked at because it's very important to us. Okay? They're very business driven. So they wouldn't look at anything which is nice in technology, which we tend to do, or very nice in products, which a lot of companies need to do, but they're really market driven. Okay? So if going to the base station and configuring the base station takes me a lot of time and money, now this is bad news. We have to address that. Okay? They didn't care whether you use LTE, LTE, Wi-Fi, whatever. They really don't care. They just really looked at the operational side from a business point of view. So they came up with use cases which they fed from day one into 3GPP. So since 2006, they have been giving to 3GPP feedback what they think is really important to make your system up and running. Having said this, often these were the very same people, okay, which solves a little bit the communication problem. It's not like one set of people developing a set of specification, handing it over to another set of people. Often these were the same people, but under a little bit looser governing body. Okay, so that goes to 3GPP, and 3GPP has been reacting on that. And if you look at the use cases which NGMN has been developing for the self-organizing networking paradigms, you can essentially distinguish three blocks. The first block is really the block related to the installation. Okay, this is all about the installation process, you know, to make sure it is when you go there, you don't lose any time in making your base station up and running. This one here, the second one, is once you have it up and operating, you're doing the final configuration test before you actually make it work. Okay, so that is a kind of self-configuring before ramp-up. And that down here is a self-configuration during runtime. So they have essentially come up with all these features here, and you will discuss a few of them. So just to mention a few, so the plug-and-play installation, what you really want is you go with the base station, you download automatically all the software updates, a bit like when you buy a new Mac and the Mac has been maybe stored in the storage house for a few months, and by the time you switch it on, there's an update in software. So you do an update in software at home. They're doing exactly the same. There's no difference. Okay? Hardware equipment run by software and firmware, which needs to be updated. Now, you don't want to do that manually. You have neighborhood relationship updates, etc., etc. And then as you go on, you know, the cell outage, load balancing on the run, etc. So we will talk about this later on. So I want you to understand that everything we talk about in a 3GPP context today has come originally since 2006 from the NGMN, simply from their experience of running cellular networks on a daily basis. Just to remind you a little bit, we had this graph also a few times these days, how 3GPP is structured and who was responsive to the information given by NGMN. So I remind you there are different technical specs group in 3GPP. We have the radio access network and the service systems are on the core network, okay? And they have subgroups essentially, working groups. And those groups which have management elements in there are the groups which were responsive to what NGMN had to say. Okay? So these were not the groups where you specify what type of modulation scheme you use or what type of coder, interleaver, etc. But these were really the groups which managed some part of the network. Okay? So this is RAN working group, radio access networking group 3, and the service architecture telecom management working group 5. These are the two groups which are responsive to that, absorbed that, and started writing technical specifications, which then got into technical requirements. This is the actual flow of the design process. So here you are. This is where it was absorbed, and let's go a little bit through the releases. How did that self-organizing networking manifest itself in the various releases of 3GPP? So we started well before 2007 with release 8. And we are currently working on release 11. And since release 8, okay, so the first kind of LTE release, a lot of SON features have actually appeared. And they appeared with a degree of headache. So release 8, it's the earliest release on that, concentrated only on the functionality of installing your base station. Okay, so it's a hardware issue. So the question here was, how do I automatically upload and download the software? How do I make an inventory? Because every base station has different hardware elements. Okay, you may have 3 antennas, you may have 5 antennas, you may have a coax cable which has this and that property, 20 meters long, 5 meters long, whatever. And you don't want this engineer at minus 30 degrees typing in this information into a computer so it goes to the operation management of the operator. You want this automated. So this is what it does. Okay, so that is a download of software. This is the upload of the inventory. So they know what this base station has and is doing. And then there come a little bit more interesting things here, which relate a little bit to what is happening in the network, because every base station needs to know who is around. Okay, so you place the base station in place and you need to know, okay, if I'm here and I have a user and this user goes out of my cell range, to whom do I hand over? How do I do that? Well, if you just ramped up the base station, then the base station doesn't know who's around unless you hammer in the neighborhood's IDs manually. Now, this is something silly to do. It's very silly to do because, and we talk about this later, you may have a lot of different base stations so you have around you, so you have to type in a lot of numbers. You don't want to do that. Also, if one of your neighbors goes in outage, or you go in outage, meaning you have to be replaced or you're out, then you don't want to go to all the neighbors and say, okay, this person has got out. So you have to keep this neighborhood table up to date without doing it manually. And how to do that has first been specified in Release 8. There's also we talked about the ID assignment. Now, in my opinion, 3GPP has failed a little bit on the specs for the PCI, which is a physical cell ID, because we just have 500. 500 cell IDs sounds like a good idea if you have a macro cell, if you have a microcell, maybe even a picocell network. But when we start talking about femtocells, where you may very well exhaust very quickly in your neighborhood the 500 cells, that becomes a headache, and we had some interesting solutions to that. But in my opinion, it's a design failure, not being able to actually project the growing numbers of base stations. So that was Release 8. Release 9 Release 9 moved away beyond the E node B as a physical entity and looked now at networking operations, so the interaction between E nodes B's and users. So this is what Release 9 did. So they looked at optimizing the handovers, doing some load balancing, the radio access channel, ROC, abbreviated. You will see that a lot if you deal with 3GPP specs. It's a very important notion, and we'll talk a little bit later about this, why this is so important. So they did everything which is about, the dynamics of the network. Anything related to my neighbors, my interaction with my neighbors, people going through, etc. This is what Release 9 did. Release 10 moved away from a single network and looked at overlay network. Okay, so if you have a macro cell and a micro cell, how does that go? How do you load the traffic forth and back? How do you optimize it in an automated manner without you spending time to actually configure the system? So again, there were coverage and capacity optimization tools, enhanced interference control, etc., etc. Loads of self-healing functions, and energy savings came in for the first time, and that's something interesting. I'm going to talk, that's going to be my last technical slide today, actually. So energy savings is something very hot at the moment with a lot of potential for improvement. So Release 10 was the first LTE marketed release. So I'm not 100% sure that Release 10 is able to meet the requirements of LTE-Advanced, but this is what is being marketed. Now Release 11, we are at it right now, and this is really about heterogeneous networks. So 3GPP has recognized that meeting the capacity demands with a single system, which would have been the nice thing, is impossible. So they recognize there are going to be heterogeneous systems ranging from different 3GPP systems to wireless LAN, femtos, etc., with different management capabilities, different management requirements, and well, the degrees of freedom just shooting up again exponentially. So here SON, I think, will really play a very central and fundamental role. How do you manage these really very wide spectrum and gamut of different technologies in a manner so you don't actually notice that there's a network in the background? Because you only notice that there's a network if it fails. Okay? Otherwise, it's a ubiquitous thing. And when you take the mobile phone and you call somebody, you don't think, now, what's going to happen with my cellular network? It's just part of our daily routine. Unless there's an outage, unless you get a call drop, unless you get a call rejected. So if we group that a little bit, what I've just told you, and going back to what I said before, so we have the radio access network, working group 5, and the service architecture, working group 5, RAN 3, and service architecture, working group 5. Over the releases, you see that there was a lot of gravity on the radio part at the very beginning. Okay, simply because, everything related to the installation of the node, etc., was a radio issue. But things are shifting lately. So there's a lot of SON functionality now actually coming to the networking management. And if we go through the points, so ANR, I've put you, by the way, whenever I can, I've put you down the abbreviations down here because I know that you're not very familiar with that. So ANR stands for Automatic Neighborhood Relation. You see, I have to look it up. And we'll talk about this. PCI is the physical cell ID selection. MLB is the mobility load balancing. You have the mobility robustness optimization. You have the radio access channel optimization, self-healing, energy savings, minimizing the drive test. We'll talk about this as well, MDT. So 3GPP has also come up with an abbreviation for that. So you have loads of different issues which arise whilst you plan, install, and run your network. And this is essentially here in these releases. Let's come to the elements. So the question is, where do you do the self-organization? Where do you take the decision? Okay. In fact, this is the second question. The first question you have to ask, what type of information do you take? In fact, they're really different. Okay, so you can very well take all the information of the network you have and process it in a distributed manner. You just have to share all this information with everybody. you can take all the information and process it in a centralized manner. You can take part of the information, do it in a centralized manner, on a distributed manner. So there are lots of degrees of freedom how you can actually run the SON, but 3GPP is rather interested in where do you take the decision, because this is where you're most likely going to be gathering the information from. Now you have clearly the localized, distributed, and centralized approach. Localized means you take the information which is around you and you draw a decision yourself. It doesn't mean for E node B very specifically, so my base station, it does not mean that it only has to take information which the base station itself sees. It could ask the mobile terminal to provide it information which the mobile terminal sees, but it can only ask the mobile terminals which are associated with that specific E node B. Okay, so the localized in the 3GPP sense means that my E node B has information about its cell, can process that information, and can do something with that. Okay, so if you see that one of your cell users has a very weak field strength, which you get with the link quality indicator, you go down in modulation index. This is a local decision you want to take. There's no need to involve a central entity placed somewhere 200 kilometers from here. That's something very local. You can decide right there, and this is done today. In contrast, the distributed one means that you take essentially information which is available to you also from your neighborhood. And here, neighborhood, we understand all the information which is coming from the neighboring E node Bs. So it means you need to talk to your other E node Bs. Now, there are different ways of talking to your neighbors. If you know your neighbors and you have a direct connectivity between them, so most likely through a logical link, like the X2 interface, you just request that information, you get the information, and you know what to do. An example is the load balancing. Okay, if I'm very loaded and I have a good connectivity to my neighbors, X2, I'm requesting, guys, what's your situation? Do you have any load? The neighbor says, no, I have nothing. So you're handing over some users to this guy. This is some of the things we could do with the distributed kind of decision taking. If you don't have a direct connectivity between the user, your neighboring base station, but you know it exists, you can always go through some central entity, so you don't have to use the X2. And if you don't know whether there's a neighbor there, you have to use your mobile phone. So most likely, you know, Jesus' phone talks to me, and he knows my cell ID, but he has functionality built in automatically, which is scanning for other neighbors. So he knows that there's also another neighbor with another base station there with a certain ID, and he reports that ID to me. I'm comparing to the IDs I have, and I see I don't have this neighborhood list in here. I don't know that this guy exists, the other base station exists. So I'm starting to initiate you know, a request to figuring out who that is, how can I talk to this neighboring base station. So that is essentially the three ways of getting this information in a distributed manner, and then you take decisions in a distributed manner. Again, the decision taking can have different phases. Okay, you could have distributed decision taking based on the same algorithm. Okay, so both base stations, base station 1 and base station 2, uses the very same deterministic algorithm to take decisions. Okay, you take them in a distributed manner, but you know that you both rely on the very same thing. Alternatively, you could have a true cognitive approach where you say, you know, my base station 1 learns completely independently from my base station 2 to take decisions. You could do that as well. Okay, but you're sharing only local information. So you do that. That would be the distributed one. And then the centralized one means, you know, you're gathering a lot of information from all your network, trying to take a decision and make sense out of that. From an optimality point of view, that's the best thing to do. If you really are able to collect all the information on time and you have a good algorithm in there, NP-complete or not NP-complete, whatever, you know, you can draw a very good decision very quickly. And then you have hybrid approaches, which are actually the practical ones. So let me just visualize that. You have essentially your network here. These are your cells with your base stations. And then you have what we call, you know, these management centers, the O&Ms, the operational management centers. That's your government in a sense. Okay, so that's typically in the operator's offices as a huge operating center which is managing the whole or having information about the whole cell. Now, centralized means everybody down here reports what's happening on a very regular basis, goes up, draws a decision, the decision taken comes down, they execute, and we hope it's going to work. A distributed one means we take the decision down here based on neighborhood information, but we still feed back some higher layer information. Okay, it doesn't need to be now exact snapshots of my state of a system. It can be some general states, you know, load is good in my cell, load is bad in the other cell. So we can, you know, my operating center has a little bit of an idea what's happening. Now, in the localized, I have exaggerated a little bit, so the link to the operating system is still here. But what I wanted to say is that you just take information from the cell to draw the decision right there, right instantaneously. Okay, like the power control, like the modulation index you use, like the channel coding you use, etc. So that's all done here. And then you have hybrids where you just share different degrees of decision taking. Okay, so for the centralized one, time is something very important, and I think we will be hearing about this in Ali's presentation later on. Because we understand that, you know, collecting a lot of information from the whole network requires or a lot of bandwidth, which we don't have, or a lot of time, which often we don't have because the decision you may take may also already be too late. Okay? So at least for the centralized one, 3GPP introduced 3 different time notions. Okay, so these intervals. The first interval is the collection interval, meaning at what time frequencies do you collect information. And as you can see, it's 5 minutes. So we're not talking about milliseconds here, so we can't operate on a transmission interval. So 5 minutes. This is really much quicker than my manual installation, which happens every 1 month, 2 months, 1 year, 2 years. So we have gone down already by orders of magnitudes in terms of reporting. So the network operating management center knows now much better what's happening in the system. It's quasi real time, and this is what it is. Now then you have the analysis interval. The analysis interval is where you try to make sense out of the data you gathered. It's typically a multiple of the collection interval. You may not want to have it, but it is recommended to be in multiple. Why? Because you want to draw decisions which are somehow weighted on past observations. Okay, just to make sure that, you know, the decision you take is a good decision. It's not a rush decision you do. So it is recommended to stretch the analysis interval to a multiple of the collection interval. And then the change interval is the one which allows you essentially to change parameters every now and then. So one change interval, which could be almost like the analysis interval, is maybe a load balancing issue. Okay, you decide, okay, cell load has to be loaded off from this cell to this cell. This can be executed very quickly. On the other hand, if you want to change the electrical antenna tilt, that is something you can't do every 5 minutes or 10 minutes. Okay, because the impact can be much larger. So you may do this every half a day or whatever. So depending on what you're trying to optimize, your actual reaction time might be different to the analysis time. So therefore, the third notion of having this in 3GPP. What are we trading? If we go from centralized, which is our paradigm yesterday, to distributed, which is our paradigm today, to maybe, you know, localized distributed, which might be our paradigm tomorrow. Well, the first thing we see is that you do things, as you get down from centralized to localized, you do things quicker. You can do things much quicker because you don't need to feed all the information up, do the process, and come down. So speed is an issue. Another important issue is the single point of failure. Meaning if your centralized entity just breaks down for whatever reason, that's it. End of the story. Okay, your system is an outage, and this is what happened with the BlackBerry. Okay, BlackBerry was a bad system design because they had just very few singular operation management centers in the world, and everything has gone through there. It breaks down, people get really angry and change operator manufacturer. So here you see the impact real world, what really happened. So you want to try to minimize these point of failures, and one way of doing that is to replicate your decision taking, but this is expensive. On the other hand, if you have going from localized to centralized, you're able to collect more information about your network. Therefore, inherently, the more information you have, the better decisions you can take. Okay, so that is essentially the trade-off. And trading all this speed, you know, your point of failure, the ability to gather more complete information, you figure out that actually there's no single optimal solution here. So what networks do today and networks will be doing together tomorrow is they will have a lot of functionalities done in the centralized, a lot of functionalities done in the distributed, and a lot of them done in the localized. It's just important to split them properly, understanding this trade-off. So if we look at the localized one, this is something we can do really on short-term statistics. You know, everything which is like short-term RM can be done here. So your schedulers, etc. The distributed one is a little bit slower, typically between two different cells, at least two cells using X2 interface. You do here handover decisions, load balancing, maybe your rack optimization, etc. And then on the centralized one, well, that's really long-term. It's your whole system. You may take, you know, the statistics of the lunch, of the evening, of a football game into account and do certain changes to your network. You do coverage optimization if you're a coverage hole. So this is essentially done right here. So the 3GPP service architecture group tried to make sense out of that. Okay, they tried to formalize it. And they came to the very same problem which the artificial intelligence, the game theory, the machine learning community had before. It is just really, really difficult. It's very difficult because there's no clear line between global, local, you know, distributed. Loads of parameters impact each other in a contradictory way. So just to give you an example, the load balancing. Okay, so if you look at the NM stands for network management, so you can essentially have load balancing and handovers actually contradict each other. So if I'm really fully loaded and my cell beside is very lightly loaded, I would like to hand over users. But maybe these users are out of the coverage zone as I would have typically defined from my other cell. So while load-wise I would like to load off, but in terms of coverage, the other one can't take it because he's still out of reach. So we are contradicting each other here, okay? And there are loads of decisions in the network where one parameter would go against the other parameter. So what we do is, well, how they came around this, they said, okay, everything which is centralized really at a very high level, at the network management level, is something we can pseudo-standardize. We can say, all right, if parameters come up here and you have to take a decision about the global load balancing, not instantaneous handover decisions, for instance, just global load balancing, that is something we can standardize, and that's being done. Everything as we trickle down the network, you know, the eNodeBs, connectivity, etc., that is something we leave still open. I think they're very cautious with that. So they also introduced the primary and secondary targets. A target is essentially, you know, something you want to achieve. Let's say you want to ensure that the interference you generate to another cell does not exceed 3 dB. That's one target. Okay, so that's your primary target. But maybe your secondary target is, you know, the load you want to give to another cell should not exceed 20%. So these are the targets. We have now primary and secondary targets, meaning that if one optimization algorithm just figures out that there are two targets going against each other, it would look essentially at the secondary target to see if it still can do something. Now, how it works in terms of the architectural approach is like this. It's very simple. It's always like this. You know, you have a management on top. you have the decision taking, you have the execution, and you have the feedback. Okay? So my network management is essentially saying, okay, is defining policies, certain policies. You know, I want when there's a football match, my traffic to be balanced better in this geographical area. This could be a policy. I'm just really giving you a high-level policy. There can be more specific policies. They're trickled down to your SON functionalities in the network. So you have an input coordination. Why is that very important? Because of this effect. Okay, so certain targets can contradict each other. So before you feed the SON algorithms with anything meaningful, you have to sort it. You have to make sense out of this data. So you're coordinating that. Therefore, you got the SON coordination at the input. Then you do your business. You do your SON algorithms, and we will hear about some reinforcement algorithms later from Maria Rita. They would be exactly here. And they come out with a certain set of parameters. Again, because they can contradict in decision taking, you need to coordinate them. So you have, again, a coordination functionality here. Once you have done it and you're good about it, you start reconfiguring your system. And then all the changes come into effect. Things happen in the network. You have changed your network. Therefore, you measure it, you observe it, and you feed it back into your SON algorithm. Okay, so that's all they do. And that is maybe the blue frames are the architecture blocks maybe you recognize as a SON algorithm designer. And this is how it is mapped to the 3GPP language. Now, how have we done that within the BeFEMTO project? And this is now very specifically to the home eNode B. I don't want to come into discuss all these points here, but just for you to understand, you know, each home eNode B has essentially layers. We're familiar with that, the OSI layers, and there's one part which goes to the network, essentially ensuring that my eNode B, home eNode B, my femtocell is able to talk to other femtocells, is able to talk to the operator, is able to talk to whoever it needs to talk, and on the other hand, it is able to talk to the user. Okay, so we have essentially two stacks here which communicate with each other. And this is a new thing. So we have a very strong SON functionality building block here in BeFEMTO. So there's a lot of stuff being done in terms of the optimization of the self-optimization. So RRIM stands for Radio Resource Interference Management. And the ones which are in red are new. So that is new stuff which we have added within BeFEMTO. So there's new admission control, new mobility control, new energy savings, whereas the load balance is something we have not touched. And today in the afternoon, if I have time, I will introduce you to a few SON-enabling functions like positioning, coverage estimation, synchronization, which also go all in there. So what we have done is essentially we have taken this high-level block and we have transformed it into the typical layered architecture which we as engineers are used to. Okay, so we have the different layers with the different interfaces, and this is where we place essentially the SON algorithms. Okay, and maybe tomorrow Giuseppe is going to present a little bit more on this architecture, a little bit in more details. I'm not sure what he has planned. So let's talk about the features. And we simply come back to what we talked before. So there's no magic, as I said. It's very intuitive, everything. You got the planning, deployment, the optimization, and the maintenance, and now you want to automate it. So let's come to the automatic planning. Before that, just for your information, I've left the NGMN and 3GPP features which are currently in each of them: automated planning, self-configuration, etc., etc. So I'm going to do this right now. I'm going to talk about some of them as we go through the presentation. The automated planning is something which started actually quite a while ago, and there was a very good European project called ICT Momentum, which has worked very strongly on the automated planning for UMTS networks back then, but I would guess it would hold also for the LTE networks. So what we have done before is GSM, what you typically has done is you have a few important parameters in the network of your base station, which is the placement, which is the beam orientation, which is the tilt, and the power you transmit. That's more or less the most important thing you have. Okay, so these are the 4 dimensions you're optimizing. Maybe well, there are a few others, but these are essentially the ones which really have an enormous impact. And you simulate that. So a system level simulator, we had yesterday presented how that works. You have a look whether that works. If you're happy, you go to the field and you deploy your system as you have actually inputted it to your simulation. If you're not happy, you take somebody who has a really good experience, and literally this is what happened. So people who had a very subtle know-how about how one parameter would influence another, they would go back, they would tweak a parameter, they would rerun the simulations and see whether that works. And until the end, that it works more or less. Now, things, of course, changed over time. You can automate the whole process. But what you really cannot do here, because this is literally NP complete, and that's the only place where I agree that you can't do it, is because every time you change a parameter here, you need to resimulate. And the simulation itself may often last for a week. Okay, it's a whole network. CDMA, one base station influence, base station in London influences essentially the power control in Edinburgh. So you have to simulate literally large areas, and this takes a long time. Now, to make it fully automated, we understand it's possible, but it is actually much more complex than you think, because you need to reverse the whole problem. Okay, you need essentially try to find the optimal configuration, okay, the optimal configuration given certain requirements. And you can't do that by simulation alone. So there's a lot of mathematics behind here. And I worked actually in France Telecom quite a lot on the outage, okay, because outage is one of the most important parameters you optimize within the system. And outage essentially comes down to shadowing, and shadowing is something which we academics we don't like it because it's, you know, it's this logarithmic term and the exponential. It's something we can't deal with, so we don't do it. But in reality, this is really what matters. Fading doesn't matter. Nobody cares about fading in the operator world. Nobody. Okay? This is absorbed by the channel coder and all the physical layer stuff. What really is important for the networking optimization is the shadowing. But academics have shunned away. So we have been trying very hard to inverse a lot of shadowing problems, which would allow you to automatically configure a certain parameters. Okay, so with my then student Philippe, we have a lot of stuff on that. So automatic planning is now used very often in the cell optimization. Now, once you've planned it, you roll it out, you know where to put your base station, and you know more or less what the parameters are. So you have an existing node B here, and your planning tool told you, okay, we need a new one here with all the constraints you have, because you can't mount an E node B where you may want to mount it. So you put it here, and then the whole problem starts. You know, you don't want to manually now configure the whole thing, so you need to set up really secure tunnels to your management platform. You need to get all the neighborhood parameters, etc., etc. So that is essentially what we're doing. Authentication, meaning this E node B is really my E node B. It's not a fake operator who's putting in E node B. Address allocation, so you're able to actually identify that E node B. It needs an IP address, it needs a cell ID, it needs a whole set of IDs actually, which in my opinion is also a failure of the 3GPP approach, because they should have actually just worked with a single ID, which may have been the IP address, whatever, you know, or the MAC address, or whatever it be. So therefore, you need a whole set of address allocations. You need a tunnel setup, a secure tunnel setup to your operating center, software installment, inventory, transport parameter setup, radio parameter setup, and then the self-testing. This is what you need to do in this phase. Then comes the actual self-optimization. Now that's the interesting part, and this is really where a lot of intelligence has been put in 3GPP lately. So it's the automatic neighborhood relation, rack optimization, load balancing, energy savings, etc. There are a lot which are not in there yet, but they're most likely going to come into the release 11 or beyond. So there's an opportunity here, guys. If anybody of you works on quality of service, quality of experience, there's very little SON functionality in there. Okay, so there you can still tweak a lot of things on the admission control, congestion control, etc. Now, when it comes to the last point, which is self-healing, there's essentially failure recovery and cell outage compensation. And failure recovery, well, it's a complicated thing, because you have to think is that you have some E node B running there in the field, and it suddenly stops reporting and you don't know what happened. It could be either because your E node B is really faulty, okay, something has happened. Most likely the E node B itself will not have realized that it has a problem, so it died before it is able to report that it is about to die. Or the link between the E node B and the management center is just broken. So these are two things which can essentially lead to the fact that you have a failure there, and you need to recover from that. What you don't want to do is you don't want an engineer to go down and try to figure out whether this base station is still alive. What's the problem? So therefore, all the mechanisms needed to recover that base stations are very, very important. And the other impact is if your cell really goes in outage, then you have to compensate for the coverage hole. Because let us take this example here. You have a base station with 3 sectors, another base station with 3 sectors, another one with 3 sectors. And they have a coverage area which looks like more or less what is realistic. It's not a circle, it's kind of these funny shapes. And let's assume that sector B goes in outage, so therefore this dark one here suddenly disappears. And what we see is that sector C and A still can help, okay? Also the base station 2 and base station 3 can help, but there will be areas where there's nothing, okay? There's literally a coverage hole. So you need to make sure that once your sector B of base station 1 has gone in outage, meaning it doesn't work anymore, that you have tools in place which automatically actually detect that there's going to be a small coverage hole here and that you do something about it. Okay, you can do different things about it. You can increase power, your rack, your control power. You can tilt more or less. Okay, you can bring up the tilting, etc. So there's different things you can optimize, and I'm sure maybe a little bit later we're going to hear about some of the opportunities we have. Where in general, a general rule of thumb is not to change the tilt as long as you can do. So touching tilts is something which is considered to be a little bit dangerous in cellular network design. Okay, so then you have all the procedures in place which allow you to detect whether something is in outage or not. So let's go to some functional details, really. We've talked quite a lot about the self-configuration, so I'm not going to talk about this again. Let me just talk about the automatic neighborhood relationship. This is since release 8. That's very important. It's actually one of the most important SON features in 3GPP today. And how have things been done before? Before, the cellular operator has kept one single table at a central station, okay, the operating management center, about the whole neighborhood relationship of all the base stations. So it would essentially, from your point of view, keep a 2-dimensional matrix with all the IDs in one direction and all the IDs in the other direction. And then if there's 1, it means they're connected. If there's 0, they're not connected. Okay, that's okay. For GSM, you can do that. With a few thousand base stations in Spain or in each country, that's all right. Things get a little bit tricky as the number of base stations increases, as you start to introduce femtocells, as you start to introduce maybe also Wi-Fi into your whole network, because you need to know also the connectivity between those to facilitate the vertical handovers, etc. So tables grow. And with growing tables, your ability to react to changes, etc., goes down, and the overhead actually reporting the table down to the base stations becomes more problematic. So the best thing to do is just to do it locally, all right? Just to do it there, let the base stations sort out their neighborhood relationship themselves. That's all right. It sounds like an easy deal, but in fact, it's not that easy. Why? Because if you introduce a new base station, this new base station doesn't know who's around. It doesn't know any IDs. It doesn't know any IP addresses. There's just no idea where it is, what it's supposed to do. Okay? If you do it manually, you would just say, okay, I introduced a new base station. It goes up to the operating center, introducing a table. This table would tell you which ID it will get and which IP address. You configured manually. It's all good. Okay? But it's an overhead, so you want to automate it. All right, so how do you do it today? Well, you listen first of all, when you switch on a base station, the base station would start listening in who's around. So it can do that. Okay, it can listen to the other base stations which are around, but it may not necessarily hear all the base stations. Okay, I'll just give you the example. Sorry, I'll give you the example I had here. Okay, so this base station, this sector here may start listening, and if it is lucky, it will hear this base station. Okay, if the power is a bit larger, it will know, okay, there's a base station right here. So that's the first thing you do. You start to listen who's around. Often you don't figure out who is there. So you start using the mobile phone to do this business for you, because that mobile phone, which is placed in a mutual coverage area, is able to see you and is able to see your neighbor. So therefore, there are all the protocols in place which allow you essentially to discover your neighborhood via the mobile phone. You then piggyback that to the operational management, and it will tell you whether this is a base station which you're not allowed to remove from your table. It's a base station which you're not allowed to do a handover to. It may also be. It might be a base station which has different features. So you know that there's a base station. You request its ID, you request its IP address, and once you have its IP address, you're also able to communicate with it directly. Okay, so these are the features which you're trying to do, and it's quite important because you keep essentially your neighborhood table completely local. Then the PCI, so the physical cell ID allocation, as I said before, it is, in my opinion, a failure in the design of the 3GPP standard. There are only 504 addresses. Okay, so they group them in 168 groups with 3 entries each, and they build the 504 PCIs. And the PCI is used to facilitate a lot of things. Not everything, but a lot of things. It's all good, you know, your UMTS network may just do well, LTE maybe as well, but as you start introducing femtocells, you get very quickly into collision, actually. So you may assign the very same PCI to nodes which are in a neighboring relationship, and this is causing a lot of problems for mainly the mobile terminal, because it doesn't know where to go, essentially. You know, it has a PCI which is the same. All right. So therefore, eNode B, as it ramps up, will not take a PCI which is doing one of these 3. Either it will not take a PCI which is reported by a mobile terminal, UE, okay, user equipment. It will not take one which is reported via the X2, clearly. And it will not take one which it can hear automatically. Anything else, it would take probably either a PCI value which is done deterministically through a deterministic algorithm, or it would randomly choose one from a pool of PCI addresses.
Sure.
Yes?
This PCI is per operator?
No, it's per sector.
Per sector.
Yeah. So you have one per sector. And it is essentially, it's a shortened ID, which I think was the reason why they introduced that, but it's bringing a lot of headaches essentially, because it can lead to a lot of overlap. In fact, there's quite a high probability of collisions in terms you're choosing, an eNode B chooses a PCI which is the same as a neighboring one, the moment you have more than one eNode B in the neighborhood. So they have done the calculations in 3GPP, so there's a round 3 document there where they calculated, you know, what is the probability of 2 eNode Bs in an area choosing exactly the same PCI, given each eNode B can choose from a pool of 10 PCIs, 50, 100, or 200, okay? Which is quite useful in femtos, okay? So in Femtocells, if you say the overlaying macro cell, maybe some microcells, maybe some picocells, get 506 PCIs minus maybe 200, okay? And the remaining 200s you have, you assign them to your femtos which are in the area, and let them choose randomly a PCI without making a lot of fuss. And they calculated the probability of any of the 2 choosing the same. It's not 0, but it's very far from 100% either. And maybe algorithms which you had proposed will help even further of getting it down close to 0. Another issue which is important is the mobility robustness optimization. It's about handovers. So handovers is one of the most complicated things in cellular networks, and I think that is really the competitive advantage of 3GPP community with respect to the IEEE community. Okay, so IEEE community has all been about data rates. If we think about Wi-Fi .11, if we think about WiMAX .16, etc., whereas 3GPP has been mainly about power efficiency of the terminal and the ability to hand over without any problems. They're really good about that. And there's a lot of documentation about how to do the handover right. Unfortunately, a lot of things can go wrong with the handovers. And even today, it happens that you just get an outage as you travel with your train, with the car, etc., etc. So what can go wrong? I'll just give you 3 examples. You know, you do a handover too late, you do a handover too early, or you do a handover in the wrong cell. Now, what can happen if it's too late? What happens? You are associated to eNode B1, and you travel with a certain speed. It turns out that the speed you travel is higher than what the eNode B estimated. It means that you're going to be out of the coverage area of that eNode B quicker than it can estimate. So it is essentially not quick enough to hand over to the next eNode B. Okay? So therefore, that could be a major problem. Another problem is if you do it too early, it turns out that you're traveling through a little coverage island here, which happens very much in urban environments because you have streets which act as field strength cannons. So it may happen as you walk or drive with your car, you drive along one street and you get into the coverage area of another one. Your system is very quick. It can hand over essentially to this new cell station, new base station, but by the time the handover is completed, you're again out of this coverage range. So you did it essentially too early in a sense. You should have waited a little bit more to see whether it makes sense to hand over. You could also hand over to the wrong cell ID. So if we take the very same scenario, but to complicate things, there's another cell which actually starts to be active in this area. Okay, and you should have actually you should hand over from this one to this one, but you hand over to this one here. So it's too late, it's too early, and it's also to the wrong cell. There are loads of different combinations. So I'm just showing you the intra handovers, meaning between the same technology. There are the inter handovers, which means between different technologies. So you add another degree of freedom. So you get hundreds of cases here where things can go wrong. And therefore, 3GPP has spent a lot of emphasis on automizing this process because, of course, one thing is, you know, the hysteresis curves. This is how you would do it, essentially. You know, you would build hysteresis curves which decide how long do you wait until you hand over. Loads of parameters. I'm going to mention some of these. They will be different for every single cell. They will be different for every single eNode B. Okay, because one eNode B might be in this scenario, another one might be in this scenario. So the whole hysteresis, the configuration is different. And it's a lot of things which you cannot simulate. You can't get it from your planning tools. So it's important to do it in the field, on the run, based on real-time information. Well, it's very simple, really. And, well, it's not that simple. The procedures are simple. It's essentially based on something which is called RLF. You know, the radio link failure. So what 3GPP has introduced is essentially a debugging tool. So you get, you know, the same as Microsoft. If one of your programs just shut down unexpectedly, you are free to send a logging report to Microsoft to see what has gone wrong. Now, the operators have exactly the same right now. So they are able right now to, your terminal is able to report if something has gone wrong, including a lot of parameters. I don't want to go into details, but it will include a few parameters which is fed back to the operating center or to the eNode B. It can optimize using algorithms which are up to us. It's up to the operator. It's up to the manufacturer to make essentially a better decision next time it happens. So this is essentially what happens. So you have a certain target coming from your management system. Okay, it says you should not have a handover failure more than 1%, 10%, whatever you want to set. So you want to keep people happy. At the same time, your eNode B reports how many you really have. And then you get the instruction to do something about it and what you can, for instance, change really over time, as you can change the trigger threshold, meaning beyond which field strength do you hand over, the time to trigger, how long do you wait, the hysteresis curves to avoid the ping pong effect, etc., etc. So there are loads of parameters you're free to choose, which sounds like a good idea, but as I told you before, the more degrees of freedom you have, the more complicated it becomes for an engineer to draw a good decision. Okay, so therefore, voila, I think there's still a lot of scope there with the handover optimization. The same with the mobility load balancing. So what is happening here? The load balancing, essentially, we talked about this before, is that you may have one cell which is very loaded, another cell which is lightly loaded, and the first question is how do you detect it? So it's detected on 3 essential degrees on the radio usage. So you request from your physical layer and from your scheduler, you try to figure out what is a load on my resource blocks. Okay, we have talked about this in the last days. Uplink, downlink. You get a load on the hardware in general and on the transmission network. Okay, so what is the load in the network, in the backhaul, etc. And also the cell capacity at large. So you get 3 indicators. They're all related. Okay, there's no doubt. They're not independent, but it gives you essentially a little bit of a backup here. So you get 3 indicators telling you about the load of the system, and then you're free to hand over essentially your users, and this is what it happens essentially. You have a serving eNode B, you have a target eNode B, you have your operating center, which is telling you how good you should perform. Okay, it's your manager, tells you, you have to have this target at the end of the month. This is what he's doing. And that is a decision taking here, really. And you can essentially tweak the handover parameters. You can say, okay, I'm going to hand over somebody if the SINR is maybe 10 dB worse or better than what I had said before. So you can load people forth and back. Okay, so that's a quite interesting option for the load balancing. Another one is the radio access channel. Now that's a very important one. It's a feature which runs through the whole 3GPP family. So UMTS had it, it was really important. LTE is having it, it's really important. What is a radio access channel? A radio access channel is a channel you use to say, hello, I'm here, I want to establish a call. Okay, so it's an uplink channel. And it essentially determines how many, if the call establishment is successful, it determines how many people a base station can take. So therefore, controlling the access and the response to the radio access channel is very important. It gives you an ability to load balance. Because imagine I'm a user, I'm trying to access my eNode B1, which has a very good field strength to me, and I'm saying, I would love to have radio access to this base station, and it turns out that my base station is overloaded, so it just says to ignore you. Okay, it just says, I don't want to hear anything about you. You figure out there's, it doesn't want to hear anything about me, so you're going to the next one. So these are the type of load balancing schemes you have. Also, the radio access channel is essentially configured using some parameters in the downlink. Okay, so the base station is sending some parameters in the downlink of how your RUC should behave. It will tell you, how much power you should transmit at, what is your retransmission schemes, etc., etc. And so all in all, the radio access channel, because it's a hello channel, you're saying hello, how you doing, etc. It's important to optimize it because it allows you to balance essentially your network. And in release 10, they've started working, release 9, they've started working very strongly on that one. Another one is the minimized drive test, MDT. What is happening here? In a real network, once you have planned it, you put the base stations and you have it up and running, an operator would still go out there and just verify that everything is okay. So they would actually take the car, have a car which goes around, measures the field strength, and they were driving around and trying to figure out whether everything is okay. If there's a coverage hole, they would reconfigure the network. Now that's an enormous overhead, and you may have a base station failure. You have loads of things which change over time, maybe even during the day, and you can't have your engineers driving around trying to figure out what's happening. So you want to automate that. So one way of doing that in a very simple manner is because you could just use a kind of crowdsourcing paradigm, in a sense that the mobile phones which we are using could report the field strength automatically. And that's a paradigm which is coming now more and more. So whilst you talk, or whilst you not talk, you're actually recording the field strength of the surrounding E-node Bs, and later on, either immediately if you're connected, or later on if you're in idle state, you're reporting essentially the field strength. You say, what was the field strength of this particular E-node B at that particular space? So the operator gets a real-time picture of the coverage holes and can act on that. Okay, I think we're maybe gonna hear a little bit about this later in Ali's presentation. So there's a lot of things you can optimize here, simply getting the feedback from the users as they use the system, and that is facilitated by a set of protocols within the within the new releases. And then there's another one, which is the coverage and capacity estimation, which is I'm my pre-last slide, I think, yes. So it's very similar to the MDT, so I'm not gonna dwell on that. What I wanted to talk a little bit about is maybe the energy saving. So that is something which is becoming very fashionable lately, because it turns out that paying the bill, the energy bill, is something which is very worrisome to the operators, because to maintain your E-node B costs a lot of energy, and the question is who's paying the bill. And we have seen that probably the only real meaningful reason of meeting the capacity demands is to making the cells smaller. So every time you halve the radius, you have to quadruple your amount of equipment, so your energy bill also goes up by a factor of 4. And that, in fact, was the original reason why femtocells were introduced. Okay, nobody likes to talk about this, but I happen to know that some operators here in Spain, they said, okay, we want to offload the energy bill to the end customer. Because if you have a femtocell, it's not the operator who's paying the electricity bill. It is you who's paying the electricity bill. So they have solved one of the problems. Now, still they have the problem, and therefore they thought, okay, if I'm able to control a little bit my energy consumption, that would be a great thing. And the only meaningful way of controlling your energy is, to minimizing your energy, is to switching off your base station. Now, if you switch off your base station, you can't serve the user, so you have a problem here. But if you design it well, okay, if you know that in the evenings there are times when your capacity demands are very low, and you are able to hand off everybody who's in my cell to your neighboring cells, you just go to sleep. Okay, you just switch off, and this is where you really save energy, and that is what is happening. So this cell briefing, this cell sleeping, that is something which is now coming up, and I don't think there are many solutions out there today, so it is worth investigating that type of line of research. So let me conclude. We all agree that self-organizing networking gives you a lot of benefits. Okay, it gets rid of manual labor. It facilitates unprecedented things. You can optimize the system in real time based on real-time, quasi-real-time data. It saves you a lot of operating costs, a lot of capital expenditure. And I've shown you just the building blocks, the understanding how 3GPP understands self-organization today. I have not dwelled on the actual embodiments of the algorithms, which is something which you need to do, and which we'll be hearing a few examples later on. Thank you very much.
Thanks for a nice presentation. Do we have questions?
No questions. Yes.
Yes.
Thanks for your talk. It was very nice. I have a question about the PCI collisions that you talked about. I think the problem is not that simple, because when you have this time frequency grid, you have to, of course, put pilot symbols in there, and you have to know the positions of them a priori. And right now it's done with this PCI. So you know the PCI and then you know the location of where they exist. And you have only a very few possibilities. So they're cyclically rotated every 6 resource elements.
Okay.
So there are only 6 possible positions actually.
Okay.
So people will have to think about not just moving away from PCI, but completely rethinking the air interface, I think. So it's probably not a question from me, but just an additional statement.
No, very good. Yeah, I'm not experienced in this, and I've also reused that particular slide here from Manuel and the one before actually. The only thing I can repeat is that I think it was. I mean, if I see 504 choices for a network where you may have an enormous amount, I see this as a failure in design. It's the only thing I can say. So it turns out it's even more complicated. Yeah. Okay. Yes.
So thanks for the talk, very nice. So I have a question regarding the user behavior. Okay, would this be included, for example, in self-organization? For example, like now more users, like for example, would like to download music in the morning and stuff like this. So sometimes your user behavior should be included somehow in the. Should like some, for example, like if the network knows like most of the users downloading music or certain users doing some heavy downloading at certain time, can they like manage that you can give him like better capacity, or maybe can start in the beginning, or maybe can do some like prediction and download some things from the beginning so that when he can start using it. So these kinds of issues should be included in self-organization, or is not included?
Well, it's a good question. It should be included. It should be included, and but it has a few problems. I tell you why it should be included. I mean, one of the things you said is, and we thought a few years back with Vasilis and King's College we observed that something very interesting. You have some trenders in the internet. Okay, so there are some people who fire out a certain link, a video link, YouTube link, and they have a lot of followers on Facebook, on Twitter, and then suddenly everybody starts watching this video link. All right. So if you know who the trenders are, and you know who the followers are, and you can match that information to the location of the followers, you could preload the video which they're about to watch. They don't know yet that they're going to watch it, but we know, because we know that they're following. We have been following the trender more closely than they have. We load it essentially to the eNode B, and we load it even down to the terminal. Okay, so they wouldn't even notice that. Now that would be like the ultimate way of doing it. Where's the problem? And one of the reasons why 3GPP clearly is not looking into this right now. You're mixing personal and technical data. It's always a bad idea. It has privacy issues, etc. Most likely you will have to go through escrow accounts. So nothing of this is stipulated, standardized, or done in any way. So from an R&D point of view, I think it's great. It may happen in the near future, but the choice so far has been, to get out of this user-centric knowledge, concentrate on the technical side, and rather over-provision or further optimize the system.
Thank you. As a follow-up to this question, I would say that 3GPP doesn't tell operators what to do. So this feature, for example, would be great, but 3GPP specs just say, this is what you have to comply with if you want your equipment to be 3GPP certified. Whatever vendor designs this system probably will be the one who will succeed. The operators will buy their equipment. So right now you already have the functionalities in the SON building blocks to report this data, at least load, time where this load reaches its peak. So it's up to the operator to make the most of it. So people tend to assume that 3GPP has to specify absolutely everything. But 3GPP just tells you how to comply with the standards. That's it.
Yeah, I see. Apart from this, yes, apart from that 3GPP tells you the building blocks essentially, I think the biggest problem I see is that you're mixing personal data and technical data. And even though maybe the managing entity might be one thing, which might be Telefonica or Vodafone, you know, there are different houses, different computers, different different management ways within the same company for these two things: the personal data, okay, where you could follow the trending, etc., and the technical data. So I see it very difficult to mix that personally. You know, I might be wrong. It's doable. You can do it, but I think it's difficult.
Okay, if there are no more questions, let's thanks Misha again.
Okay, thanks.
And let's be back in